Hi, welcome to the start of the Euclidean Geometry 101 course. We'll be focusing on the domain of plane geometry, which means that we'll be staying in a two-dimensional plane. This is the geometry that is treated in the first 6 books of the ancient mathematician Euclid of Alexandria. The works of Euclid can arguably be called the most important mathematical textbook ever written. Only the Bible has seen more prints. Euclid is called the father of geometry, though the contents of the Elements, which is the name of his 13-volume work, have their basis in earlier works that are all but forgotten. As with so many works of antiquity, the originals of the Elements have been lost, and the transcripts we possess are from several centuries later. Neither do we know much of Euclid's life or how he looked. Though many of the proofs presented in the Elements are his, the material presented was mostly prior knowledge. The real merit of Euclid is that he systematized all the earlier knowledge in geometry and number theory and compiled it into a logical framework that is still a masterpiece today. We will construct this course in a similar way. The method that is used in Euclidean geometry is known as synthetic geometry. This method, also used by Euclid himself, starts from axioms and builds up the theory by using properties to prove theorems. It is a method that does not use coordinates at all. This is in contrast to analytic geometry, which uses algebra to pose and prove theorems. The reason why I prefer to use the synthetic method is twofold. First of all, it is an excellent method to practice logic. And secondly, one tends to lose oneself in the equations of the algebraic method, while Euclid focuses on the visual construction and its properties. The lessons presented here are based on a French-Dutch mathematical book by Dalle and De Waele. So without further ado, let's begin with Lesson 1, by laying the groundwork of plane geometry, its axioms and postulates. In mathematics, axioms and postulates are the starting points for the various branches of study. They are the basic statements one must assume to be true. Some of those assumptions are self-evident, and one can ask why they should be stated. They are stated so that it becomes possible to build the whole collection of theorems of the field in a logical way and without room for doubt. They are thus not proven, because they form the basis and the constraints within which the whole field of study resides. Though the two terms axiom and postulate have mostly the same meaning, within Euclidean geometry there's a clear difference. An axiom is something which is a statement about something that is common knowledge and obviously true. The postulates in Euclidean geometry are more about discovered constructions that are assumed to be possible. Euclidean geometry is based on 5 postulates, 2 of which we'll need right away. In order to talk about the postulates of Euclidean geometry, it is first necessary to define some concepts. In plane geometry, we consider the properties of objects in 2 dimensions. 2-dimensional objects, called surfaces, have 2 measures, length and width. 1-dimensional line objects only have 1 measure, which is length. Euclid called a line something with length, but without breadth. A point is an object that has no dimension and no measure. It is in fact the notion of a location in Euclidean space. Among the lines in the plane, the straight line is arguably the most important and the basis of the first two postulates. The first postulate states, one can always draw a straight line from one point to another point. The second postulate states, a finite straight line can be extended continuously in both directions. These two postulates actually describe the basic operation of a straight edge. To be able to construct the logical framework of Euclidean geometry, Euclid also included 5 axioms concerning very common notions. The first one: if one thing is equal to a second thing, and a third thing is also equal to the second thing, then the first thing is equal to the third thing. Many among you will know this as a transitive relation. The second one: if equals are added to equals, then the wholes are equal. The third one: if equals are subtracted from equals, then the remainders are equal. The fourth one: if two things completely coincide with one another, then those two things are equal to one another. And lastly, the whole is greater than the part. So through these notions, immediate deductions can be made using the postulates. The first postulate can be restated as, 2 points determine exactly one straight line, or in other words, 2 straight lines coincide completely if they have 2 points in common. Now let's continue by naming some planar objects. A line segment is the part of a straight line between 2 points. 2 line segments are equal if they can completely coincide. Adding 2 line segments together is the same as placing one line segment in line with the other. The sum of 2 line segments on the same straight line is the segment connecting the endpoints. A line segment is greater than a second line segment if it is the sum of that second line segment and a third one, and so we call the second line segment smaller than the first one. Points that lie on the same line are called collinear points. A broken line is a line that is not straight, but consists of parts that are straight. A broken line whose beginning point and end point coincide is called a closed line or a polygon. A curve is a line that has no part, however small, that is straight. Any combination of points, lines, or curves lying in the same plane is called a plane figure. And that's what we are going to study in this course. This is the end of part 1. In the next part, we'll introduce angles and a third postulate. If you like this series, consider subscribing to my channel.